Hi, everyone. I'm Sijun. I'm a PhD student at UC Berkeley, and today I'll be presenting MPCAuth, multi-factor authentication for distributed trust systems. So nowadays, we have seen a lot of growing interest in distributed trust systems from both academia and industry. And typically, in such a distributed trust system, the client possesses some secret X that she wants to protect from and securely stores. And instead of storing it on a centralized server, she will split the secret X into secret shared forms where each of them looks random, and then distribute this secret shares to multiple servers so that none of the server actually sees the data. Later, when the servers want to perform computations on the data, they will leverage cryptographic tools such as MPC, which stands for Secure Multi-Party Computations, to allow them to privately compute on the data without reviewing the data. And distributed trust system is more secure because the attacker now needs to compromise all servers in order to recover the client's secret. There are many applications of distributed trust systems. One particular example is cryptocurrency wallet. So in this case, the client's secret is the digital asset that she wants to protect. And instead of storing it on a centralized server, she will split it as secret shares on multiple servers. And later, when she wants to authorize transactions, these servers will engage in an MPC protocol to produce a digital signature validating the correctness of the transaction. And there are lots of other applications such as collaborative machine learning and secret key recovery as distributed trust systems. So in all of these systems, the user has to perform some kind of authentications. For example, in the cryptocurrency wallet case, the user needs to first authenticate to prove to the servers that she is indeed herself before she could have the servers authorize transactions. So one central question is how do we authenticate to these distributed trust systems? One Strawman approach is that we can have the servers authenticate to one master server. And we assume that other servers just trust this master server. However, this approach will introduce a central point of attack because a malicious attacker can compromise this one single server to recover the secret. So to ensure security, the clients need to authenticate to all servers. Another approach is to have the clients authenticate to each of the end servers. And this approach definitely avoids the central point of attack. However, it adds a lot of burdens on the client side because the client now needs to authenticate to n servers n times m times, considering we have n authentication factors. And this is a huge burden on the client side. Let's give you a more concrete example. Let's consider email authentication, and the client wishes to authenticate to multiple servers. She will first initiate requests to multiple servers, and each server will compose an email with a passcode to the email server, and this email server will forward all of these emails to the client. So the client, in general, has to check n emails and enter this passcode n times, and which is an extremely burdensome user experience. So how can we design a system so that the user only needs to authenticate once, just like the way they did in a traditional system while maintaining distributed trust? We present our solution, MPCAuth, which is an authentication system for distributed trust applications in which the clients only need to authenticate once. We support many commonly used authentication factors such as email, SMS, U2F, passcode, biometrics. And one amazing additional property of our system is that it is profile hiding. That means it hides the user's authentication profile such as your email username, phone numbers, passwords, and biometric features. In a typical centralized server, when the user registers for some service provider, she will necessarily have to provide to the service provider these authentication profiles. We show that in our work, we can actually leverage the distributed trust infrastructures to have the servers authenticate the clients without even reviewing these authentication profiles. Before we dive into our talk, we'll first briefly mention the threat model. So we consider a maliciously secure model where the attacker can corrupt up to n-1 out of n servers, and the attacker will try to impersonate the client. And security holds if the attacker cannot successfully authenticate as an honest user if at least one server and one authentication factor is not compromised. So due to the time limit, in our talk, we'll only focus on the email authentication protocol, which is the most technically challenging and interesting. For other protocols, please refer to our full paper. So in a traditional email authentication workflow, the client will initiate an authentication request to the application server. This application server would then compose the email with the passcode and send it to the email server over a secure TLS channel. And the email server will forward this passcode to the client, the client would check this passcode, read it, and enters it into the app, and then forward it to the application server, and the application server would check if the passcode matches. If it matches, it will let the user authenticate. So now, instead of having one single server, we have multiple application servers. And somehow, we have to figure out a way to let this multiple application server send only one single email to the email server. Our main insight is that these end servers can jointly act as one single logical server to interact with the email server, where inside these logical servers, they will run MPC. And inside MPC, they will assemble an email with only one passcode and send this encrypted emails as encrypted packets over the TLS channel. So in the end, the email will be encrypted and send it and forward it to the email server. So the interesting thing about our construction is that MPC is normally used to compute a single function. But here we're using MPC to simulate a logical server that is engaging in an interactive protocol, which is the TLS protocol, with an email server that is running normal local computations. And somehow this email server that's performing local computations thinks that it is actually talking to one single TLS, regular TLS client, where it is in fact talking to multiple application servers. So one core building block in enabling our construction is the TLS and MPC protocol, which we will go over in high-level detail, at a high level. So at first, the servers will engage in the TLS handshake protocol, where they jointly perform Diffie-Hellman key exchange with the email server. And in the end, they will obtain a secret share of the secret key, which is used during the data transmission phase. And then during the data transmission phase, the servers would jointly run an authentication encryption scheme to encrypt these messages and transmit them over the network. And they will run this encryption scheme in MPC with secret share, secret key, and messages. The TLS and MPC protocol is extremely powerful because when the client registers for the service, she will store their data as secret shared on the server. So the data is secret shared at rest. And then during data transmission, this data is encrypted inside MPC with a secret shared encryption key. So none of the servers actually see the encryption key, and what they see is the encryption of the messages. And any one of the server can just forward this encryption of the messages to the email server. And so during the entire process, none of the servers actually sees any plain text data. And this is exactly why we're able to build our profile hiding constructions for many of our authentication protocols. And this TLS and MPC protocol is itself extendable to other use cases beyond authentication. So now with TLS and MPC, we'll build our email authentication protocol, which works as follows. First, the client will initiate a request to the application servers, and each application servers will sample a random passcode S. And inside MPC, they will jointly compute a joint passcode S using their local randomness. And in the meantime, they will compute in MPC a PRF of S each individually. So each one of them has a unique PRF, which they later use to verify the client. Then they will use the TLS and MPC protocol to send this email to the client. The client will receive this passcode S and enters it into her app. And then the client app will compute this, will use the passcode S to compute the PRFs and send it to each individual server. And each individual server will check if the passcode match, if the PRF matches. If it passes, it let it authenticate. And note that during the entire process, the passcode S has to be hidden from all servers to ensure security. So in this email authentication protocols, the client only needs to enter the passcode once on the client app. And also, the client's email username is hidden from all servers. This is because when the user registers for the service, the email address is stored as secret shared on the servers. And when the users, during data transmission, when sending an email, this email address is also hidden in a TLS in MPC protocol. So none of the servers actually need to learn the email address to send an email. We evaluated our system on top of MPC libraries, MPSpeed, ENG AP MPC, and the TLS library WOLF SSL, and evaluated the system on multiple AWS machines. We showed that without an established TLS connection, that means we establish a TLS connection from scratch and then send an email, our total runtime is 12.2 seconds. However, we can leverage the fact that multiple clients share the same email provider. So we can maintain a persistent TLS connection with one email provider and send multiple emails from different clients over the same TLS channel. And with an established TLS connection, our total runtime reduces to 3.3 seconds with an online latency as 0.4 seconds. So the end-to-end user latency could be as low as this online latency, 0.4 seconds. Our system is practical, and we demonstrate it by sending an email from multiple servers to Gmail without introducing a TLS timeout. And for evaluations of other factors, please refer to our paper for more detail. To sum up, we present an authentication system for distributed trust applications. Our system enables a client to authenticate independently to end servers by doing the work of only one authentication. And we design secure, practical, and profile hiding protocols for multiple authentication factors. Thank you.
Any questions?
So, great talk. What happens if those servers are compromised? Do we just lose the 2FA stuff, or do those servers get my Gmail password, for example?
They will not get your secrets. One of them may went down. It would just do a denial of service or something, but they will never get your secret.
Even if they're actively malicious?
Yeah, so even if n-1 servers out of n are malicious. So unless
all of them are.
If all of them are, then you get your secret, yeah.
Cool, thanks.
This is super cool. So is the idea that you're doing all of the AES GCM under an MPC, or is there some trick that makes it fast so you don't have to do that?
You did have to do it under MPC, but I think AES is relatively fast today in MPC as well. So yeah.
Okay, thanks.
All right, hi, cool talk. So I just want to confirm, when you have the comparison between already having an established TLS connection and not already having an established TLS connection, that connection also had to happen under MPC, right? You can't just take an existing, one of the servers can't already have a TLS connection because the key had to be, okay, cool.
Yeah.
All right, thanks once again.
Thank you.